doesn't work here. Oh, no, okay. The part 3 we'll discuss later. So the conclusion of this part 3 is that the best conversion speed is something like 1/t, which is, if you think as a statistician, is quite good. If you think like an optimizer, it's not too good. So in this part, I'll try to make sense of all this. So let's go back to the machine learning problem, just some basics. Example, character recognition. We want to find the recognition function on the basis of training examples. We expect that it's going to work for all character variants, not just the training examples. So the issues are approximation, how to represent the function. Statistics, how many examples do we need to estimate the function? And another way to look at this is to say that its generalization is different from learning by rote. And computation, how to compute the function efficiently. We know that you use a training set, a testing set. We do plenty of things. And the mathematical statement is that the typical one is that the examples are drawn from some unknown probability distribution that represents the nature. That we have a loss function that measures the cost of answering y hat when the true answer is y. And we seek to find a function f star that minimizes this loss over the distribution, averaged over the distribution that represents nature. And then we have problems. First is an approximation problem. It's not feasible to search f stars among all functions. So instead, we search f stars within a family f of function that's richly parameterized. Could be extremely large, but since still it's a more limited family. And the estimation part is not feasible to minimize the expectation E of f because we don't know the distribution. Instead, we search a function fn that minimizes the empirical risk, which is the average loss over the training set examples. So in other words, we optimize a surrogate problem. There is the problem we want, and we make two leaps that transform the problem into something we can handle, but it's not exactly what we want to solve. And we have this curve that shows everywhere in the machine learning literature that basically the error we achieve by computing the best function on the training set within our family minus the best one we could ever achieve is the sum of two errors. One is how much we lose because we use a family of functions that doesn't contain everything. And the other one is how much we lose because we use a finite training set. So when the size of the family of functions increases, the estimation of error increases because the finite training set is no longer enough to specify the function within the training set. And the approximation error decreases, and the sum of the two has some kind of optimum. And well, this is something that's well established. In some cases, one minimizes penalized empirical risk, which is some coefficient times a function omega of f plus the empirical risk. And this can be viewed as minimizing f with the constraint that f belongs to a family of functions that's constrained by omega f greater than less than c, where c is determined by the choice of a Lagrange coefficient. And this is what the support vector machine is. So basically, it fits in that paradigm. So I would like to focus on the computational problem. There is a statistical perspective, which says it's good to rig the objective function in a way that ensures a fast estimation rate. Basically, that the estimation error decreases quickly when the number of examples increases. And as computer science or maybe applied mathematics or optimization perspective, well, it would be preferable to choose an optimization algorithm with strong asymptotic properties like superlinear, like one of the things that's optimized in exponential minus exponential t. And when you look at these two statements, there is a conclusion that seems a small leap, but that proves to be incorrect. That to address a large-scale learning problem, we should use some superlinear optimization algorithm and optimize an objective function with a fast estimation rate. In fact, if you perform a finer analysis, you go to a dramatically different conclusion. So let's look at it in simpler terms. There is a basic large-scale algorithm that everybody uses, which consists of discarding most of the data we have. And if you take a problem like the web problems nowadays, the data comes at such a rate that it's impossible to process them all. So you discard most of them. And compared to that baseline large-scale learning algorithm, the question is, what is the statistical benefit of processing more data? And what is the computational cost of processing more data? And how do we balance these benefits and these costs? So we somehow need to link the statistic and the computation. So in the 60s, when Vapnik and others worked on statistical learning theory, well, they don't discuss computation at all. It's out of their perspective. In fact, they didn't have computers. In the 80s, there is Valiant, and Valiant defines learnability, and because that was also the time of the development of complexity theory, he excludes exponential time algorithms from the definition, which is quite different from I would say that's probably the main difference with the Vapnik setup. But it turns out that the polynomial time, that's already quite slow. If you have to wait like number of examples to the power 12, I'm not going to wait. And there are a few results that actually use that part of the pack theory. So one way to do it is to be extremely simple and to say, well, our problem is to compute the minimum of the empirical error, and this is costly. Since the empirical error is a surrogate function, well, why do we need to compute its optimum exactly? It's already the wrong function to start with. So we're going to assume that we have some kind of approximate optimizer that returns some f tilde n, which is within rho of the optimum. And rho is a parameter that we're going to adjust. For instance, if you have an iterative algorithm, you could decide to stop it early and save computational time at the expense of accuracy. So when we decompose the error, we have a third term. So basically, the error we get with this algorithm minus the best we could ever get is the sum of something we lose because we search the function in a family that's less than everything, something we lose because we have a training set of finite size, and something we lose because we don't optimize perfectly. And our problem now is to choose the family of function, the number of examples, and the accuracy to make this sum as small as possible. But we have constraints that I call the budget constraint. And the constraints can come in typically two categories. One of the constraints is the maximum number of examples that you have, and another one is the maximum computing time. So that gives us an opportunity to give relatively formal definition of what is small-scale learning and large-scale learning. So this is a kind of optimization problem, and we know that the solutions are going to be dramatically different depending on which constraints are active or not. So I'm going to say that this is a small-scale problem when the active budget constraint is the number of examples. So I'm constrained because I have few examples. And I'm going to say this is a large-scale problem when the active budget constraint is a computing time. Well, there are cases where you could have both, but that's corner cases. So let's look at the small-scale learning problem. If my constraint is the number of examples, well, I can reduce the estimation error as much as possible by taking all the examples. And I can reduce the optimization error to nearly zero by optimizing till the last digit I can get on my machine. Time is not the issue. And I'm left with adjusting the size of the family of function, which is the classical situation we have in machine learning. So in the large-scale case, it's more difficult. Now, if the active budget constraint is the computing time, the trade-offs are more complicated. For instance, if I decide to optimize more, to choose rows smaller, I'm using some of my time. Therefore, I cannot see as many examples, or I have to use a simpler model. So the way this trade-off works is that it involves the optimization algorithm. When I say a sentence like this, if I reduce the accuracy, so if I reduce row, meaning that I'm making my optimization more accurate, I need more time. And how much more time is something that depends on the optimization algorithm. And to save this time, I need either to have less examples or I need to use simpler models. And both these things depend on the optimization algorithm. So that makes things a lot more complicated. But on the other hand, that also gives an opportunity, which is an opportunity to speak about optimization, to speak about the speed of optimization algorithms from the learning perspective and not from the optimization perspective. So here is an example of my problem. On the y-axis, I have the test error, and on the x-axis, the computing time. So if I take a fixed system and change the number of examples, so the dot, dot, dot is the limit that represents the optimum. If I have few examples, it's going to go quite fast because I can optimize quickly. But when I give more and more computing time, there's just so much I can do because I don't have enough examples. When the number of examples increases, I basically go slower, but I can go lower. So I have a bunch of curves like this. Now, if I change the statistical model or I change the optimizer, I get a bundle of curves like this. And a good learning algorithm would be one that would be on that boundary here. This is what I want. But depending where I am, I'm going to use different models, different number of examples, different optimizers. So the simplest way to analyze this is to look at the asymptotics. So we have this decomposition of the excess error. The excess error I'm making by using this approximate optimization on this training set, on this family of function minus the optimum is the sum of three terms. And the key of the asymptotic analysis is that we should decrease all these terms with comparable rates. Because if we force one of the errors to decrease faster, basically it's lost, but that represents computing efforts. So if I want to do it with minimum computing efforts, all the three should be about the same. There is no reason to force any of these terms to decrease faster, because that wouldn't decrease the order of the excess error. So we need to look at the details. So there are some complicated uniform convergence arguments that say that this sum is has the same asymptotic behavior as the approximation error plus log n over n to power alpha, with alpha between 1/2 and 1, plus rho, the optimization error. And in fact, there are three types of bounds that go there. You have the classical VC bounds, where you have a square root of 1 over n, and they're known to be pessimistic. You can tweak the VC bounds in the realizable case when you know that you can reach a training error that's 0. You can change them into 1 over n. And you have a bunch of localized bounds that make slightly stronger assumptions on the distributions. So there are some things with variance and the Tsibakov condition that are basically in 1 over n, log n over n to the power alpha. So there is a I say a little industry in making this fast approximation rate bounds, but the essence is this. It's basically they all land the result that has this shape. Now, since we said that all these three should be asymptotically equivalent and decrease at the same speed, that means that we should have all these at the same speed, and they should be equal to log n over n to the alpha and the same as rho, because there is no reason to make the accuracy much more than this term. And there is no reason to make this term much more than the accuracy. So we get this massive equivalence that represents the sweet spot. Now the question is about the optimization times. Now we have to look at the other part, the time to do the optimization. So we have this gradient descent algorithm. We have the stochastic gradient descent. And I'm going to consider two more, which are Newton's algorithm, where I replace the gain by the inverse of the Hessian. And that's pretty optimistic because I assume I know the Hessian. If you have to estimate the Hessian, it's actually slower. And the second order stochastic gradient, where I insert the Hessian, the inverse Hessian, before the gain. And here is the table. Gradient descent, time per iteration n, number of examples. Because I have this sum, I need to go over all the examples to compute the gradient. Well, the second order gradient descent is also n, it's the dominant term. The multiplication by the Hessian is not a big deal in comparison. For stochastic gradient descent, the time per iteration is 1. And for second order stochastic gradient descent, in terms of the number of examples, order 1. There is a hidden term there, which is that I have to multiply by the Hessian, which has the dimension. So the dimension has a weight here. Number of iterations to reach a certain accuracy. For gradient descent, is logarithmic in 1 over the accuracy. For second order gradient descent, is log-log in 1 over rho. That's this superlinear optimization algorithm. For the stochastic gradient descent is in 1 over rho, and for the second order is in 1 over rho as well. So time to reach a certain accuracy, I have to multiply the two. And now I have to use my equivalences. So if I go back here, I see that the error is 1 over n to the alpha. There is the log here, fine. And I try to express everything with the error there. And what I see is that the time to reach a certain error, excess error, sorry, for the gradient descent is like 1 over the target excess error, 1 over alpha. And that's assuming that the n grows the right way, that at every point with this algorithm, I choose the right number of examples, I choose the right accuracy, so everything is chosen right. If I go to Newton, well, the log terms are different, they're slightly better, but the dominant term is still the same. If I go to stochastic gradient descent, well, I know that rho is the same order as the error, and second order stochastic gradient, rho in the same order as the error. So the first thing that we notice here is that from the point of view of optimization, time to reach a certain optimization accuracy on the training set. Well, the second order gradient descent is much better than the gradient descent, which is much better than the stochastic gradient descent or in any variant. But when I look at the time to reach an excess error in terms of generalization error, which is my goal for training, well, this time, well, the second order gradient descent is not much better than the gradient descent. You have these log terms that are different, but log term. And the stochastic gradient descent, well, it's not only is nice, because it doesn't have the log terms, but it doesn't have the 1 over alpha. So basically, under the conditions where we use the stochastic gradient descent, we have something that's equivalent to one of these fast rates of convergence. So, so basically, it seems to learn faster. Now, the question is it true? OK. So let's benchmark stochastic gradient descent on some problem. Yes? Okay, these ones are assumed unknown. The 1 over rho is what I try to do with my calculation. I'm going to redo it right tomorrow. This is something we've seen. Basically, we know that the error of gradient descent decreases exponentially. Yes?
Yes. Okay, actually, yeah. I just was wondering about the log n over n, the estimation error. Where did that come from?
This one? It comes of all these results. So there is a lot of literature behind of each of these lines.
And that's linked to the estimation error of the log n over n, the alpha? That's relevant.
This one here?
Yes.
Well, the thing is that people looked at estimation error and they try to look at the complex of approximation plus estimation error. So there are results that try to put them all together already. And if you look at things like the Vapnik-Chavonenkis bound, there is a result on the estimation error, and you consider approximation error fixed. So, yeah, you want to know whether this thing, there isn't a one-to-one correspondence here. It's not true. I'm sure I'm answering the question. Can you repeat the question? It comes from all this literature about the estimation error. It comes from the Vapnik-Chavonenkis bounds. And essentially, it comes from statistics. When you do statistics and you try to compute something on the basis of data, typically, if you assume independence, you get a rate in 1 over square root of n. When you compute a mean, you get a rate in 1 over square root of n. Now, it turns out that in statistics, if you do things right, and a bit more subtly, you can go sometimes in 1 over n. There are some examples, like for instance, if you compute paired confidence intervals, you get 1 over n instead of 1 over square root of n. So when you run the machine learning derivations, and you do all the statistical analysis of machine learning, the calculation seems quite horrible and complex, and that it can be very hairy, but it's the same basic phenomenon. Basically, if you don't do anything, you just barely correct, you're going to be in 1 over square root of n. If you're a little bit smarter and do things right, you can go in 1 over n, but you cannot go much faster. So you can see this as saying that when you have estimation error in the play, basically, you are really limited by something that's 1 over n to the alpha, with alpha between 1/2 and 1. Sometimes you have a log that comes here, that just, but it's not a very significant term. Yes?
Here we have error estimation is related to kind of exponent function, right?
I beg your pardon?
I can see here that you come up with the results on error estimation on log function, right? Somehow related to exponent. Do we have any ideas why it's exponent function?
I'm not sure I understand the question. I'm sorry.
Why it's log function?
Why do you have a log in there? Okay. There is a lot of debate about this log. The typical Vapnik results have a log, and there is a technique that allows you to remove it. That's, what is it called? I forgot. So there is a technique that's a different proof technique that allows you to remove it. So people wondered whether the log was actually real or not. In some derivations, you just don't have it. Typically, if you want a bound, you're going to have the log. If you want an expectation, often you can remove it. Often. But I cannot tell you whether it's actually always there or not. Manfred would know that. Sometimes, he says. Okay, so basically the essence of this slide is really that now you have to deal with statistics. And statistics is something in 1 over square root of n, or 1 over n if you do it well. So when you want to be effective, you have to have all these errors that decrease the faster you can, but all together. And the faster you can for the statistical one is 1 over square root of n or 1 over n, or something like that, in between. So when you go back to this, and you say, well, no, the row, there is no point to choose it too small, because if I choose it too small, I'm going to make the optimization error extremely small, but the other ones will remain large. Therefore, it's better to take the row not too small so that I can process more examples. And when you replace, you're just computing this exact balance. And the exact balance tells you that, well, stochastic gradient looks good now. Vichy, how much time do we have?
You could go on a little bit if you want. We have 30-minute breaks. The break starts at 10:30, but since we took a little bit longer break. Or if you wanted to stop here and then come back to the experiments.
Yeah, I'll do the experiment next time, I believe.
Okay, so then let's stop.
So, well, break. Because in 30 minutes, well, if I rush, I can do it in 30 minutes, but it's not good to rush.